Hello students, in this video we'll use the Fourier transform to find the solution to the Laplace equation with initial conditions on the upper half space. So the problem we're going to consider is the following. We're going to look for a function u of x and y such that uxx plus uyy, that's just of course just the Laplacian of u, in two dimensions is equal to 0. Our domain is going to be x over all real numbers, negative infinity less than x less than positive infinity, and y is going to be greater than or equal to 0, so we're on the upper half space. And I'm going to give you an initial condition that u of x and 0 is equal to a function f of x, right? And I want this to be sufficiently smooth. Namely, I want f hat to exist, right? i.e. f hat to exist. Okay, so of course if f is a Schwartz function or an infinitely differentiable function, we can make sure that happens, that decays sufficiently fast, right? So that's the problem, so that's our upper half space, right? Here's the real axis. Here's the y-axis, right? And we want a harmonic function on the upper half space with the initial profile that u of x and 0 is equal to f of x. So this is our upper half space model, okay? And this is very important in complex analysis as well, right? Okay, so there's our problem. And so what we're going to do, of course, is we're going to do Fourier transform one of these variables over here. So I'm going to do something to Fourier transform the x variable. So Fourier transform the x variable to get, well, if we Fourier transform both sides of the equation, we're going to have what? When you Fourier transform a derivative, recall what the rule is for Fourier transforming a derivative. The rule for Fourier transforming a derivative is that if I have f k of x, and we Fourier transform k derivatives, we get a negative 2 pi I xc to the power k, f hat of xc turns into multiplication. So of course that's our rule for differentiation. And so what we get, we're going to have that when k is equal to 2, this turns into a 4 pi squared I squared, but I is negative 1. I squared is negative 1, so it's going to be a negative 4 pi squared xc squared. And then u hat of xc and y plus the y derivatives are unaffected by the Fourier transform. So that's d by the y squared. U hat xc y is equal to 0. And this, what I've done is I've turned the PDE into an ODE. This is an ODE in the y variable, right? And so what ODE is, it's a very special form of an ODE. So it is exactly the ODE what? This is the ODE that looks like what? This ODE has the form d squared. It's d squared for two derivatives minus 4 pi squared xc squared applied to the function u hat of xc and t. And these t's are y, of course. Those are y derivatives. Y is equal to 0. I know how to solve this in principle, right? I know that this is going to give me just exponential solutions, right? So what kind of solutions will we get over here? We're going to conclude from this that u hat of xc and t is going to be a function c1 of xc e to the positive 2 pi modulus xcy plus c2 of xc e to the minus 2 pi xcy, like so. Now, at this juncture, we know that this function over here is not decaying at infinity. So this function does not decay at infinity. This does not decay. In fact, it grows as y is greater than 0 and modulus xc goes to infinity, right? So in other words, this function, I can discard this function because it's decay. We know that Fourier transforms have to go to 0 for regular functions, have to go to 0 as xc goes to infinity, and this does not, so we have to punch out the solution. That's not part of my solution. So I only get this function c2 of xc e to the negative 2 pi absolute value xc y, right? So there's our function. So our u hat of xc and t is just going to be what? It's just going to be c2 xc e to the negative 2 pi modulus xc y. Okay, great. Now, of course, we wanted the Fourier transform to exist for a particular reason that when now, if I Fourier transform this initial condition over here, I get that u hat of xc and 0 is f hat of xc. That's my initial condition with the Fourier transform. And so if I plug in y equals 0, this formula turns into a 1. So I see that this c2 has to really be f hat of xc. So this is going to be f hat xc e to the minus 2 pi modulus xc times y, right? And so if I want to find my solution, I'm going to have to use the following fact that if we have a product two functions over here, so when I look at u, so u of x and y, that's t should be a y, not, I think of parabolic equations, that's my field of study, so apologies, I study parabolic PDs, right? Nonlinear, non-local parabolic PDs, so I'm going to put a y there, okay? Do I have any other t errors? Yeah, I have one more t error, apologies again. Sort of force of habit, right? You can't get over your field of research, that's a y. Okay, great. I think I have all the t's handled now. Good, okay. All right, u of x and y is going to be what? Is going to be f convolution, this p of y, py of x, right? Because I know when you have the general rule is that when you have two Fourier transforms, if I have a Fourier, for arbitrary things, if I have a hat of xc times b hat of xc, then the inverse transform of this thing over here, the inverse Fourier transform of the product of two Fourier transforms is just a convolution b of x, right? So that's the fact we're using over here. Now, of course, we know a function we did in the previous video. We've already figured out what the Fourier transform of this thing is over here. So recall now, so we know that e to the negative 2 pi modulus xc y will inverse Fourier transform to the function 1 over pi y over x squared plus y squared. That's just our good friend, the Poisson kernel on the upper half space. Poisson kernel on upper half space. Beautiful. And so now we're done. So now what we can say is we can say our solution, so our u of x and y, is going to be 1 over pi, the integral over r, of what? Of my f, we'll say f of z. That's my initial condition over here, my f, right? And then times what? The y is going to be fixed for us, so y is fixed. There's a y. Over, now we're doing the convolution with respect to the x variable over here, so I'm going to have a y squared, and then plus x minus z quantity squared, dz. And this is our Poisson representation formula. So this is our harmonic representation formula for the solution of the Laplace equation on the upper half space. Thank you very much.